Hello everyone and welcome to this video. Today we're discussing the diffraction and the polarization of light. Recall from wave optics that one of the major advantages of using the wave theory of light was that it was successfully able to explain the phenomena of interference, diffraction and polarization. So here remember that this chapter is just an extension of the wave theory of light, and therefore the diffraction explanation that we will study in this chapter is based on Huygens principle and the wave theory of light. So what exactly is diffraction? Diffraction is observed when you try to see what happens to a shadow which is cast of an opaque object. When light casts a shadow of an opaque object, you expect that the shadow should be sharp. But in reality, the edges are not sharp, but you have what is known as a fuzzy shadow. So why exactly is this happening? The answer is that light is bending at the edges of this object and entering regions which should have been a perfect shadow, but some light is reaching into this region which should have been a shadow. And therefore we say that if we look clearly at the shadow cast by an opaque object, close to the region of the geometrical shadow, there are alternate dark and bright regions. And where have we seen these dark and bright regions before? We have seen them in interference. So what is happening at the edges of an opaque object is interesting, and this is nothing but an example of diffraction. So getting a fuzzy shadow, or the fact that light enters into a region which should have been a shadow, is an example of diffraction. Diffraction then by definition is nothing but the bending of light around an obstacle or an aperture, and therefore here you can see the light has bent up around the opaque object and therefore you have got a fuzzy shadow. And it is because of this bending that light is able to penetrate or encroach into the region of geometrical shadow. And thus I say that light is deviating from its linear path. But whenever we were talking about light so far, we always said that light was traveling in straight lines. In fact, the entire field of ray optics is based on it. So how am I now saying that light is moving from its linear path or that it is bending around objects? The answer is that ray optics is valid in cases where the wavelength of light is negligible as compared to the objects which we are considering. And therefore, in the cases of ray optics, all the things that we were considering like mirrors and lenses, all of them were very big as compared to the wavelength of light. And in such cases, you can safely assume that light is traveling in a straight line. But when you start looking at objects whose sizes are comparable to the wavelength of light, then in that case, effects like diffraction become prominent. And therefore, I will say that when we are discussing diffraction in this chapter, everything that the light is going to encounter has a size which is comparable to the wavelength of light. Only then the diffraction effects really become substantial. Let's now understand the diffraction of light using a simple example of water waves and by applying Huygens principle, that is by using the wave theory of light. Planar wave fronts incident on a narrow slit will transform themselves into spherical wavefronts. This is because every point on the wavefront between the slits acts as a secondary source of waves. Here we are assuming that the slit is so narrow that there is only a single secondary point source. However, in reality, the slit will be made up of many such secondary sources. Thus you see that the shape of the wavefront itself is transformed when it encounters an obstacle which is comparable to the wavelength. The same thing happens in case of light waves. If there is no obstacle in the path of light, the planar wavefront will pass uninhibited. However, when it encounters an obstacle, you see that it bends around it. The planar wavefronts become spherical secondary wavefronts as they pass this slit. As the slit gets smaller, the bending is more. Thus, the narrower we make the slit, the greater is the spreading. Hence, it is observed that diffraction becomes more prominent when the dimensions of the aperture or the obstacle are comparable to the wavelength of light. Diffraction is then obviously most prominent when the slit width is the smallest. In principle, the phenomenon of diffraction is common to all types of waves. The diffraction of light at a single slit can be demonstrated by using the same setup as the Young's double slit experiment, but we simply replace the double slits with a single slit. So right off the bat you see that this is the major difference in the interference that was obtained in the Young's double slit experiment and this experiment. There we had two slits which were acting as secondary sources. Here you have a single narrow slit which is acting as your secondary source. The rest of the setup is not changed. You still have a primary source S which is acting as a monochromatic source of light, that is, it will give out light of a single wavelength. And all these waves which are starting from the primary source S will hit the narrow slit, that is, it will hit the narrow slit and produce secondary sources of light. Every single point on the narrow slit will act as a secondary source of light and emit spherical waves in all directions. And now you see that what we get on the screen is a diffraction pattern. It is very clear as to the properties of this diffraction pattern. You can see that there is a central bright region and this is the brightest and the biggest region amongst all the bright regions on the screen. So you have a central bright spot and on its sides there are alternate bright and dark regions, and the intensity of the bright regions is getting weaker as you go away from the central point of this diffraction pattern. So these are the qualitative characteristics of a diffraction pattern. One was that it is created by infinite secondary sources. Every single point on the slit is acting as a secondary source and therefore effectively you have infinite secondary sources, and it is nothing but the interference of the waves which is coming from all these infinite secondary sources which is giving you a diffraction pattern. So now that we have seen what a diffraction pattern looks like, let's try to understand how will I find out whether a point on the screen is going to be a point of darkness or a point of brightness. So basically I'm trying to find out a quantitative analysis of the diffraction of light at a single slit. To do this, we continue with our setup, but now as you can see, I have placed two lenses which I have added to the original setup. So the question is, why have I added these lenses? You see, when we were looking at the Young's double slit experiment, we always assumed that the incoming waves were plane wave fronts, and therefore here also I want the incoming wave to be a plane wave, that is, I want the wave front to be planar. And to make that happen, I have placed a lens L1 because the output of this lens L1 is a plane wave front because it gives out parallel waves. So L1 is known as a collimating lens and its output which will come out from the lens is nothing but a planar wavefront WW'. And it is this planar wavefront WW' that is made to fall on our narrow slit AB. So we have what we wanted. We wanted an incoming planar wavefront. Now we know that every single point on the slit AB will produce secondary waves. What we want is to focus the diffraction pattern on the screen, and for this we are using the lens L2. So L2 is doing nothing but focusing the diffraction pattern on the screen, and we know that the diffraction pattern obtained has a single central bright band and alternate dark and weak bright bands of decreasing intensity on both sides. This pattern is obtained by the interference of the secondary waves emitted by the infinite sources which lie between points A and B. Each point on the unblocked portion of plane wavefront AB is sending out these secondary wavelets in all directions. This is nothing but Huygens principle. And if I actually draw the rays of light, I will see that these rays are actually emitted in all different directions. But what I want to do is find out whether a point on the screen will be a point of maximum intensity, that is a bright point, or a dark point. What we are going to do is first analyze what is happening at the central point O. So we say that secondary waves emerging from CA and CB have no path difference, that is, they are travelling the same distance as they reach O. And hence, because they are all travelling the same distance, they reinforce each other, and the point O is a point of maximum intensity. So you see, essentially what we have done is that to analyze whether a point is bright or dark, we divided the wavefront into two halves. One half was CA and one half was CB, and we said that the waves which are coming from the part CA of the wavefront and the waves which are coming from the part CB of the wavefront, they are traveling the same distance to go to point O, and therefore they will reinforce each other, and what you get at point O is a point of maximum intensity. However, like I said, all the rays that come from AB don't go in one direction only. In fact, they are in all directions. So let's say that I want to find out whether the point P1 on the screen is a dark point or a bright point. What I have to do is draw the rays starting from the slit AB reaching point P1. When I do this, I see very clearly that the rays which are reaching point P1 from the lower half of the wavefront, that is from CB, are obviously traveling a greater distance as compared to the rays which are going from the upper half of the wavefront, that is AC. The basic idea is to add the contribution of the rays in the upper half and the lower half and check whether point P1 is a point of high or low intensity. So basically we are treating different parts of the wavefront at the slit as secondary sources. Here we have taken two sources, AC and CB. So the rays which are reaching P1 from the lower half of the wavefront, let's say for example the ray BP1 is clearly travelling a greater distance as compared to the ray AP1. And therefore the path difference between these two rays has to be calculated, that is BP1 minus AP1 will be nothing but this distance Bn. Note also that these rays make an angle theta with the central line SO. If the lens L2 was not present, all these rays would make the same angle theta. Also remember that the addition of this lens will do nothing to change the calculations of this experiment. Whether the lens was present or not, it does not affect our mathematical calculations because the lens affects all the rays in the same way, and hence we don't have to worry about what extra distance any ray is travelling inside the lens. Assuming that the slit AB has a width A, we see that the angle BAN turns out to be theta, and the path difference will then be given by A sin theta. And so the path difference between any ray reaching point P1 from the upper half of the wavefront and the lower half of the wavefront will be A sin theta, and for very small angles of theta I can approximate that to A theta. Once we have this, we can now analyze whether the point P1 is going to be a point of high or low intensity. In the first case, let's assume that the path difference between these two rays is lambda. In such a case, I can say that A theta is approximately equal to lambda. We now divide the slit into two equal halves, AC and CB, and therefore each of them will have a size A by 2. We already know that the waves coming from point A and point B have a path difference of lambda as assumed in this case. It is clear that for every point in the upper half of the wavefront, there exists a point in the lower half of the wavefront such that the distance between them is A by 2. In such a case, I see that A by 2 theta will then be equal to lambda by 2, or in other words, the path difference between waves starting from A and C or the path difference between the waves starting from C and B will be lambda by 2. And we know from the theory of interference that if the path difference is an odd multiple of lambda, this leads to destructive interference, and therefore we see that contributions from the two halves of the slits just cancel each other, resulting in point P1 to be a point of low intensity or a dark region. Similarly, if I assume that the path difference between the ray is 2 lambda, then I divide the slit into 4 parts and observe that the contributions from each of these 4 parts cancel out because each wavefront will occupy a slit width of A by 4, and for every point in the first quarter of the wavefront, there will be a point in the second quarter such that they lie A by 4 apart. In such a case, their part difference will come out to be 2 lambda by 4, which is lambda by 2, and hence they will again cancel each other. Similarly, for every point in the third quarter, there is a point in the fourth quarter of the wavefront such that they lie a by 4 apart, which means that the part difference between them will be lambda by 2, and hence they also will cancel each other. And overall again, we will see that the point is a dark point. Because of the symmetrical nature of the diffraction pattern, we are able to write the same conclusions for the dark regions lying below point O as well. And in general now I can write a formula for obtaining a dark region at a point which is nothing but the part difference should be equal to n lambda. Because if the part difference is equal to n lambda, you can always divide the slit into an even number of parts such that the part difference between all these will be equal to lambda by 2, and this will result in destructive interference, giving you a dark point. Therefore, if a theta is equal to n lambda, or in general a sin theta is equal to n lambda, you will get that the point is a dark point. In contrast, if the part difference between the rays starting from point A and point B is equal to 3 lambda by 2, then the slit is divided into 3 parts. Now, the part difference between the secondary waves from corresponding points in the first 2 parts will be lambda by 2. This is because for every point in the first third of the wavefront, there will be a point in the second third of the wavefront such that they lie a by 3 apart. And if they lie a by 3 apart, their part difference would be 3 lambda by 2 divided by 3, which is nothing but lambda by 2. Thus, the first 2/3 of the wavefront will interfere with each other destructively. The third part of the wavefront, however, remains unused, and thus this intensity reaches the diffraction pattern on the screen and gives you the first secondary maximum. However, because this bright region was formed only by 1/3 the wavefront, the intensity is weak. Similarly now, if the part difference between the waves coming from A and B is assumed to be 5 lambda by 2, we'll have to divide the wavefront into 5 different parts such that each of them occupy A by 5 width, and there will still be a part difference of lambda by 2 between each of them, such that the first 2 parts of the wavefront will interfere destructively and the next 2 will also interfere destructively and cancel each other, but the last or the 1/5 of the wavefront will still produce intensity on the screen, which will be your second secondary maxima. And because only 1/5 of the wavefront is producing this intensity will be even less as compared to the first secondary maxima. In general then, the condition for producing a maxima will be that the part difference A sin theta should be an odd multiple of lambda by 2. And therefore I say that A sin theta is equal to 2n plus 1 lambda by 2 is the condition for a maxima in the diffraction pattern. From the intensity curve of the diffraction pattern, it is obvious that the magnitude of intensity of the central spot is the largest. We can also find a formula for the width of the central maximum. It is simply the distance between the first secondary minimum on either side of O. If capital D is the distance between the slit and the diffraction pattern on the screen, and small f is the focal length of the lens, we see that the width of the central maximum is given by the formula 2d lambda by A or 2f lambda by A, where f and d are assumed to be approximately the same. From this formula, it is clear that if the slit width A decreases, the width of the central maximum increases. The angular width of the central maximum is given by 2 theta, which is equal to 2 lambda by A. This completes the analysis of the diffraction of light at a single slit. So if light diffracts when it encounters a slit which is comparable to its wavelength, why did we not talk about the diffraction of light in the Young's double slit experiment? In the Young's double slit experiment, we had 2 slits, and here when we were learning the diffraction of light at a single slit, the only difference was that we had one narrow slit. which means that even in the Young's double slit experiment, at each of the slits, diffraction must be taking place. But we just didn't know about it when we were learning about that experiment. This can be seen from the fact that if you take a look at the interference pattern from the Young's double slit experiment, we know that a pure interference pattern will have bands equally spaced, and we also know that the intensity of all the bright bands will be exactly the same. But when you actually observe the interference pattern obtained from the Young's double slit experiment, you will see that the intensity of the central maxima is more than the intensity of the secondary maxima. And this is not something that is a characteristic of the interference pattern. This is actually a characteristic of the diffraction pattern, as we have just seen, which means that in reality, the interference pattern obtained in the double slit experiment is limited by the diffraction pattern obtained from each single slit. Diffraction is taking place at each of the two slits, and this diffraction pattern obtained from each slit is actually superimposed onto the interference pattern obtained from both the slits, and therefore we say that the final pattern that we are actually seeing is a superposition of the diffraction pattern from each slit and the interference pattern from both the slits. And therefore you can see that here the outer envelope is the diffraction envelope and inside are the interference fringes. And if the width of the slit becomes very small, then the diffraction pattern becomes really flat and we observe the interference pattern again. Why does this happen? Because the width of the slit becoming small means that the number of sources which are contributing to the pattern becomes less, and if it becomes very less, it means that ultimately you just have 2-point sources in the Young's double slit experiment, and that's just a pure interference from two sources. And therefore in the limit of A, which is the width of each slit becoming very small, the diffraction pattern spreads out, it just flattens out, and what happens is that you get the interference pattern again, that is, you get a pure interference pattern. The number of fringes, that is, you see there is a broad diffraction peak in which there are several interference fringes inside, and the number of these interference fringes depends upon the ratio D by A. That is, it depends on the ratio of the distance between the two slits to the width of each slit. That is, D is the distance between the slits and A is the width of each slit. So you see the Young's double slit experiment is affected by the diffraction of light at each single slit. Finally, let's take a look at the difference between diffraction and interference in general. We saw that an interference pattern has a number of equally spaced bright and dark bands, whereas the diffraction pattern has a central bright maximum, which is almost twice the other maximum. The intensity in case of a diffraction pattern falls as you go away from the central maxima towards the secondary maxima on either side. However, in the interference pattern, the intensity does not drop. Secondly, we also saw that interference was obtained from two waves originating from two narrow slits. The diffraction pattern, on the other hand, is a superposition of a continuous family of waves that is from infinite sources originating from each point on a single slit. So this was the difference between the diffraction and the interference pattern. One of the most important concepts associated with the study of diffraction is the concept of resolving power. Resolving power is usually defined for instruments, for example, like a microscope or a telescope, or even for our eyes, which is an optical instrument also. Resolving power of an instrument is the ability of that instrument to be able to separate the images of two distinct objects. And why is this so important? Because when these objects have a small angular separation, sometimes the instrument does not see them as separate, it sees them as one single object, and at such point we say that these images are not resolved. So resolving power is the ability of an instrument to distinctly show the image of two distinct or separate objects having a small angular separation. Let's take an example to understand what is resolving power. Pay careful attention as this motorcycle rider rides down this dark road. From very far, you see that the two street lamps appear to be as a single one. They appear to be merged. But as the rider moves closer and closer to the street lamps, he sees that these two lamps are actually separate. And this is what happens to us as well. When we look at these two street lamps from far away, they look as a single one because our eyes are not able to separate these two objects. However, on coming closer to the object, we are able to see that they are actually two different objects. This happens because when an object is placed very far away, the angle it makes at our eye is very small. Thus, we say that the angular separation of these two objects at our eye is very small when they are far away. However, as we move closer towards these street lamps, the angular separation increases and our eyes are able to resolve or separate these images, and we can see them as two separate street lamps. Thus, this angle or the angular separation is what tells us about the resolving power of the instrument. So, where does diffraction come inside this logic of resolving power? The idea is that initially at the very beginning of the chapter we saw that whenever light tries to make a shadow of an opaque object, it's not able to make a sharp shadow. It makes a fuzzy shadow. And why does that happen? It happens because light is diffracting at the edges of the object. In fact, this happens every time light tries to create an image of any object. For example, if you try to analyze the image created by a spherical lens, you'll see that the image obtained again is not a sharp image. Now, of course, in ray optics, you have seen that the image of a point object formed by an ideal lens should be a point. However, in reality, diffraction effects come into play, and the image of a single point object formed by a lens will actually not be a single small point, but it will be a bright central circular region surrounded by concentric dark and bright rings. As you can see in the diagram, we have formed two bright discs surrounded by concentric dark and bright rings. These are the images of two sharp points. But as you can see, we did not get two sharp points as the image. We got these bright round discs which occupy some space. Of course, their intensity curves are also plotted just below the image. Which means that if I bring these objects closer and closer to each other, even though the objects, which is the points themselves, are not touching each other, their discs begin to overlap. And because of this overlapping of the discs, the images of these two objects also merge with each other, and we can no longer see them as two separate objects, but we start seeing them as one single object, even though the actual points themselves are not touching each other. So diffraction tells us that because the images formed are because of diffraction, you cannot have an infinite resolution of any instrument. And how much resolution does an instrument have? And what does it mean to be completely resolved? This we know from Rayleigh's criterion for resolution. Rayleigh said that two images of two-point objects which are close to each other can be considered to be resolved, or we can say in simpler words, can be considered to be separated if the central maximum of one falls on the first minimum of the other. And you can see clearly from the intensity curves that here in this case the central maximum of one is falling on the first minimum of the other, and therefore the picture that you are seeing is the case when these two images are just resolved, which means at this point I can still see the 2 points as two separate points, but if you bring them any closer to each other, these two images will merge and we will no longer be able to see them as separate objects. So this is the just resolved situation, and similarly every instrument has a situation in which it is its limit of resolution, where beyond that it cannot resolve two objects. So this is where diffraction plays a role in the understanding of resolving power. It limits the resolving power of optical instruments. We already know that if you allow a parallel beam of light to be incident on a convex lens, then geometric optics or ray optics tells us that this lens will converge these parallel rays onto a sharp single point. And therefore, in ray optics, we learned that parallel beam of light gets converged to a single point. However, in case of the wave optics, we have just learned that because of diffraction, the beam, instead of getting focused to a single point, gets focused to a region of finite area. The length or the size of this disk is dependent on the diffraction effects that the lens undergoes. To study the diffraction effects which affect the lens, we must look at the diffraction due to a circular aperture, because a lens is nothing but an opening through which the light is coming in. So whether you have a lens or you have a hole, it doesn't matter, both of them act as circular apertures. So let's study the diffraction of light due to a circular aperture. Let's say that monochromatic light of some wavelength lambda is incident on a circular aperture of diameter d. In such a case, the pattern on the focal plane, that is on the screen, will consist of a central bright region surrounded by concentric dark and bright rings. As you can see, here we have shown the plane wavefronts being transformed into spherical wavefronts due to diffraction at the circular aperture, and what we are obtaining is an airy disk. So instead of getting the same size of the hole as the image on the screen, we are getting this airy disk which has a central bright spot, and of course there is the bright ring, and outside that are alternate dark and bright rings concentrically. So here you can see that the image which is formed on the screen is bigger than the object itself. And what is the object? It is the hole or the circular aperture itself. And the image is bigger because of diffraction effects. So these effects are the reason why the image of two objects will be bigger when formed by the instrument. And that's where the idea of resolving power came in. In order to apply the diffraction theory to the circular aperture, it is beyond the scope of this video, but we can directly say that the angular radius of the central maxima is given by the formula sin theta is equal to 1.22 lambda by small d, where small d is the diameter of the hole itself, lambda is the wavelength of light. Similarly, the path difference or the angular width of the dark fringe is given by d sin theta is equal to 1.22 lambda, or sin theta is equal to 1.22 lambda by d. Now, for small theta, you can just assume that sin theta is approximately equal to theta, and it will become theta is equal to 1.22 lambda by d. So here we found the conditions for the diffraction due to a circular aperture, and this applies equally well if you had a lens, because an aperture is nothing but an opening that allows light to come inside it. And now therefore you have understood the image of an object formed by an optical instrument is a disk as compared to a point single object. So the image is a disk, but the object is a single point. And because of this, it is important to understand what is meant by the resolving power of an instrument. Resolving power then is just the part where you still can see these two images separately. For example, here you have 2-point objects shown as two bright spots, and at this point their images, which are these two bright disks, are well resolved. That is, these not only are the two objects separated, but their two images, that is the two disks, are also very far from each other. So this is extremely well resolved. There is no problem here. But as the objects themselves get closer, their images also get closer, and as you can see, the objects have still not touched each other, but the images have begun to merge because their disks have now begun to merge. But even at this point, where the central maxima of one is falling on the first minimum of the other, this is the final limit of resolution. That is, at this point also the images are resolved, but they are just resolved. This is nothing but the Rayleigh's criterion for resolution, which means that beyond this point, if you try to bring the objects any closer, then even though the objects are still separate, the images of the objects will begin to merge, and what you'll see is one image. You won't be able to distinguish them, and in this case the objects are not resolved at all. So this is the not resolved case. So we saw that the images formed by optical instruments are limited by the diffraction effects, and because of this we have to define what is known as the resolving power of an instrument. Let's first take a look at the resolving power of a telescope. Now, a telescope is used to see the images of distant objects, that is, objects that are really, really far away from each other, which means that when the light falls on the telescope from these objects, the light is always parallel. So, as you can see here, we have two objects, which are two stars, A and B, which are very, very far away, and the light reaching the telescope from these two stars is parallel. Now, the point is that the resolution of the telescope depends upon the objective. Well, you see, the telescope has two lenses. One is an objective and one is an eyepiece. It is the objective on which the resolution of a telescope depends upon. This is because the light coming onto the telescope is captured by the objective itself. And therefore, objective is like the eye of the telescope. It is the part which is seeing what light is coming in, and therefore the resolution of the telescope depends on the objective. The eyepiece is just going to magnify whatever objective gives it to the eyepiece. So whatever goes from objective to eyepiece, the eyepiece will magnify. But if something is not clearly seen by the objective itself, the eyepiece can do nothing about it. And therefore it is important that the images formed at the objective itself are clearly resolved. And therefore, I say that stars, for example, which are not resolved in the image produced by the objective, cannot be resolved by any magnification produced by the eyepiece. It is the purpose of the objective to decide the resolution of the telescope. So if we take a look at the image formed by the two stars at the objective, we know that the parallel rays will be incident on the objective from each of these stars. The first image formed is an airy disk, as we saw, that is a diffraction limited image of star S1, and similarly there will be a diffraction limited image of the star S2. As you can see, these two are airy disks. However, there is an angular separation between these two objects, and this angular separation is d theta. And this angular separation must be some certain value so that their images are clearly resolved. So the smallest angular separation or the smallest angle which is allowed between the objects such that the images that they form are separated is given by d theta is equal to 1.22 lambda by small d, where small d is the aperture or the diameter of the objective of the telescope. From here I get resolving power, which is nothing but the reciprocal of d theta. This is because the smaller the angular separation for which the instrument can produce two distinct images, the greater is the resolving power of the instrument, and therefore resolving power comes out to be d upon 1.22 lambda. So the resolving power of a telescope is thus directly proportional to the aperture or the diameter, as you can see from the formula, and inversely proportional to the wavelength of light, because lambda is in the denominator. A similar argument can be applied to the objective of a microscope. In the microscope also, the objective is responsible for deciding the resolving power of the microscope. So here now we'll take a look at the image formed by the objective of a microscope. Let's say you have a point object. The image formed by this lens will again be a diffraction limited image, and as you can see, it is an airy disc. In this case, the object is placed slightly beyond the focal length of the lens so that a real image is formed at a distance v. Now we know from geometric optics that magnification is nothing but the ratio of the image size to the object size, and in this case I will get that m is equal to v, which is the distance of the image from the lens, upon u, which is nothing but f, which is the distance of the object from the lens. So we know that magnification is ratio of image size to object size, or it is the ratio of image distance to the object distance. So I get m is equal to v by f. And if the angle subtended by the objective at the focus of the microscope, that is at the point where the object is placed, is 2 beta, then in this case I get that d upon f is equal to 2 tan beta. You can do this by considering the two triangles separately. You will get d by 2f and you will have to multiply that by 2 and you will get d by f. So here you have d by f is equal to 2 tan beta. This is my second equation. Next we see that the size of the image formed is equal to v theta, where theta is 1.22 lambda by d. We got this from the analysis of diffraction at a circular aperture. Now suppose I have two objects and I'm looking at the two images formed by this lens. I will see that these two images are nothing but diffractly limited images, which means they are two airy discs. And when these two discs are just resolved, that is, the images of the two objects are just resolved, in such a case I say that the distance between them is r, which is nothing but what is the Rayleigh's criterion, and this distance is nothing but v theta itself. So r is equal to v theta, which is equal to v 1.22 lambda by d. So this is the distance between the two images formed of the 2-point objects, which means that the original distance between the two objects is given by d min. So what I'm trying to find out is that if r is the minimum distance that should be maintained between the images such that they appear different, what is the distance between the objects that should be maintained? That is, what is d min? And r is nothing but acting like the image, and d min is acting like the object, and therefore I can say that d min will be nothing but r upon m, and r is nothing but v theta, and therefore d min will be v theta upon m, that is v 1.22 lambda by d upon m. And here now I will replace v by m with f, which is the focal length of the lens, and therefore I will get that f upon d 1.22 lambda is equal to d min, but d by f is nothing but 2 tan beta, and therefore I get d min is equal to 1.22 lambda upon 2 tan beta, and for really small angles I get that d min is equal to 1.22 lambda upon 2 sin beta, because for small angles tan can be approximated as sin. This therefore is the minimum distance between the two objects such that the images are resolved. So r was the minimum distance between the two images such that they appear separated, and d min is the minimum distance between the two objects such that their images appear resolved. So this is the distance between the two objects that should be maintained such that we get a clear resolved picture of their two images. Now obviously if the medium between the object and the objective lens is not air, then we'll have to account for the medium in between, and therefore you add an n in the formula, and this n is nothing but the refractive index of the medium which you have placed in between. N sin beta together is known as the numerical aperture, and then resolving power is simply obtained by taking the reciprocal of d min, that is rp is equal to 1 upon d min, and now it's very clear that resolving power can be increased by choosing a medium of higher refractive index. Finally, we must also consider one important question. When does diffraction even become prominent? We have been using ray optics for a very long time and we got really good results with it. So why should I even look at diffraction optics? We should look at diffraction optics in a certain range. That is, what happens is that when light is traveling in a straight line, it is going to start deviating from its path significantly after a certain distance. So this minimum distance up to which light can travel before it starts deviating from this path is known as Fresnel distance. So light deviates from its path because of diffraction, and up to a certain point it does not deviate so much that you have to worry about it, but beyond that point you have to start worrying about diffraction effects. So we say that, let's say if the distance is much smaller than a value known as ZF, then the spreading due to the diffraction is smaller compared to the size of the beam. In such a case, you can directly use ray optics or geometric optics and not bother about the diffraction effects. However, as you move away from the source of light, it becomes comparable, and the distance approximately is known as ZF, which is known as the Fresnel distance. Beyond the Fresnel distance, the spreading due to diffraction is so large that it dominates any assumptions you make in ray optics. That is, then you have to start worrying about diffraction. So if you lie within the Fresnel distance, if you are operating within the Fresnel distance, you don't have to worry about diffraction effects. You can neglect them because they are very small. But beyond the Fresnel distance, that is ZF, diffraction effects can no longer be ignored, and you go from ray optics to diffraction limited optics. And therefore this Fresnel distance is important to decide what is the final limit of using ray optics, that is ZF is equal to a square upon lambda, where a is of course the size of the aperture and lambda is the wavelength of the light used. The second phenomena which led to the success of the wave theory of light was its effective explanation of the polarization of light. To understand polarization of light, let us consider a wave which is propagating along the x direction. In this case, each particle in the wave is vibrating along the y direction only. And because the displacement which is along the y direction is at right angles to the direction of propagation of the wave, we have what is known as a transverse wave. In fact, we have looked at transverse waves when we were talking about wave mechanics in volume 1. However, here we are talking about it in terms of light waves. We know that light waves are transverse waves, and in this case, a light wave traveling in the positive x direction will have all its particles vibrating only along the y direction. In this case, we say that this wave is a y polarized wave because all the vibrations of the particles are taking place along the y direction. Such a wave is also known as a linearly polarized wave when you consider that the wave is linearly polarized along the y direction. Linear stands for line, and therefore I say that this wave is linearly polarized along the y direction because its vibrations lie along a straight line, which is nothing but the y axis. However, the wave can also be considered to be called as a plane polarized wave because it lies in a plane. In this case, it is the xy plane. So the same wave can also be known as a y polarized wave, or it can be known as a linearly polarized wave along the y direction, or as a plane polarized wave in the plane xy. So it's an xy plane polarized wave. Such a wave which travels along the plus x direction is described by the formula y is equal to a sine kx minus omega t. You can see that the displacement of the particle along the y direction is a function of its position along the x direction, that is x, and of course of the instant of time t. Here of course a is the amplitude of the wave itself, omega is the angular frequency of the wave, and finally we also know that lambda is given by 2 pi by k, where k is nothing but the wave vector. Similarly, you can also have a wave propagating along the x direction again, but whose particles are vibrating along the z direction, which means this wave lies in the xz plane, or we say its particles vibrate along the z axis. Such a wave will be described by an equation z is equal to a sine kx minus omega t. Here again a is the amplitude of the wave, omega is the angular frequency, and lambda is its wavelength. Note that in this case the wave is z polarized, or we say it is linearly polarized in the z direction or plane polarized in the xz plane. Thus, we see that a linearly polarized wave is one which has vibrations confined or restricted only to one single direction. On the other hand, sometimes you have light rays in which the plane of vibration changes with time, and then we have what is known as an unpolarized wave. You can see that these vibrations of the particles lie in all random directions. These arrows represent the directions in which the particles are vibrating. And because these arrows are in all possible directions, this symbol is for an unpolarized wave, telling you that these vibrations are in all directions. Thus, you can see that for an unpolarized wave, the displacement is randomly changing with time. However, in all the three cases, the propagation of the wave is always perpendicular to the vibration of the particle. Therefore, even in case of linearly polarized light or unpolarized light, the direction of propagation and the direction of vibration are always perpendicular, maintaining the fact that light is a transverse electromagnetic wave. Thus, light is a transverse electromagnetic wave in which electric and magnetic field vectors vary sinusoidally, perpendicular not only to each other but also to the direction of propagation of light. You can see from the diagram, here we have two waves at 90 degrees from each other. One of these represents the electric field vector and the other represents the magnetic field vector, and these two are at 90 degrees to each other, proving that light is a transverse wave where the electric and magnetic field vectors are at 90 degrees to each other and at 90 degrees to the direction of propagation of the wave itself. For example, here the electric vector lies along the y direction and the magnetic field vector lies along the z direction, whereas the direction of propagation is the x direction. However, in general, light does not have some fixed direction in which its particles vibrate. That is, in common light sources, light propagated in a given direction consists of many independent planes of vibration which are randomly oriented about the direction of propagation. So in general, in common sources, light waves are said to be unpolarized or polarized randomly. The symbol for unpolarized light is given by an arrow and a dot, where the arrow is representing the direction of vibration in the plane of the paper and the dot represents the direction of vibration of light perpendicular to the plane of paper. And therefore now onwards, whenever we show the symbol for unpolarized light, we will use a dot and an arrow. The arrow will be the light which is in the plane of the screen and the dot will be the light which is perpendicular to the plane of the screen or the plane of the paper. So if natural sources of light usually contain unpolarized light waves, how does one even obtain polarized light in the first place? To do this, we use what are known as polarizers. A tourmaline crystal is an example of a polarizer. When incident light, which is unpolarized, is made to pass through a tourmaline crystal, we see that only those vibrations of light pass through the crystal which are parallel to its crystallographic axis, also known as the pass axis. In this case, the crystal has a pass axis lying along AB, and we can see that the incident light is unpolarized, but all the light coming after passing through the crystal is only polarized along the y direction because the pass axis lies along the y direction. So this tourmaline crystal here has given us plain polarized light and is thus known as a polarizer. Obviously, the output has reduced intensity and therefore the output of the polarizer will always have intensity less than the input. But here we see that the polarizer or the tourmaline crystal has produced plain polarized light. So we use the tourmaline crystal to produce plain polarized light. And this phenomenon of restricting the vibrations of light in a particular direction perpendicular to the direction of propagation is known as the polarization of light. Now obviously it is not necessary that the pass axis will be along y-axis. In general, the pass axis could be at any angle and only those electric field components which lie parallel to this pass axis will pass through the crystal unprohibited, that is, they will go through without being affected. All the others will be absorbed or blocked by this polarizer. The fact that light waves are transverse waves can be demonstrated by using these polarizers or polaroids. A polaroid contains a long chain of molecules aligned in a particular direction as shown by the blue chain of molecules. What happens when you make unpolarized light incident on a polarizer? You see, the electric vectors associated with the propagation of light wave along the direction of the aligned molecules get absorbed. That is, only the electric vectors which lie perpendicular to the long chain of molecules are making it through as they pass through the polaroid, as is clearly seen. All the other directions are absorbed. Thus, if an unpolarized light wave is incident on a polaroid, then the light wave gets polarized, that is linearly polarized in such a way that the electric vector oscillates only in a direction perpendicular to the aligned molecules. This direction, which is perpendicular to the aligned molecules, is what is known as the pass axis of the polaroid. So the molecules lie along one direction and the direction which is perpendicular to this molecule, that direction is the pass axis, and when unpolarized light wave is incident on a polaroid, the electric vector which vibrates parallel to this pass axis, only that will pass through. But of course the question is, what happens to all those arrows which lie between the y and z axis? Why did they disappear? You are blocking only along the z axis and the pass axis is along y. What happened to all the arrows that lie between y and z? The answer is that the electric vectors of all directions can ultimately be resolved in two directions, that is along the y and the z direction. And as you can see, the molecules are along the z direction, so all the z vectors got absorbed and what you have is only the y direction vectors which are coming through. So basically I can say that the intensity has straight up reduced to half because one half of the vectors all got blocked and the other half are making it through. So this discussion shows that the intensity coming out of a single polaroid is half of the incident intensity. We can then place an identical piece of polaroid P2 after P1. And you will see that when you place them in such a way that their pass axes are parallel, the intensity of light coming from the other one, P2, is just the same as was coming from P1. Let me remind you that the intensity of light after P1 was already half of the original intensity. And then here in this case, when the path axes of both of them are parallel, the intensity of light after P2 is exactly the same as the intensity of light after P1. However, there is a dramatic effect on the intensity of light if you start rotating P2. If you start rotating P2 in such a way that the path axis of P2 is at an angle theta with respect to the path axis of P1, you will see that the intensity is reduced even further. In this case, we understand this effect by assuming that light passing through the Polaroid P1 gets polarized along the path axis of P1, and then if the path axis of P1 makes an angle theta with P2, then when the polarized beam passes through P2, only the cos theta component of the electric vector will pass through the second Polaroid. That is, only E cos theta component passes through the second Polaroid, which means the final intensity, which is proportional to the square of the electric field, will be proportional to the cos square theta. That is, we get I will then be equal to I naught cos square theta, where I is the final intensity coming out of P2 and I naught is the intensity coming out of P1 and theta is the angle between their path axes. We see that the intensity coming out from the second Polaroid is a function of the angle between the path axes of the first Polaroid and the second Polaroid. This is known as Malice's law, and then when you change this angle to 90 degrees, it was observed that P2 is transmitting almost no light. That is, when the path axis of the second Polaroid was placed at 90 degrees to the first one, the Polaroid was transmitting no light, and from Malice's law this is obvious because cos 90 will be 0, that is, the output intensity will be 0. So remember, Malice's law was applied when you had two Polaroids and theta was the angle between their path axes. Also note that already the intensity coming after the first Polaroid is 50% of the original intensity. It's already half. But by placing the second Polaroid, you are able to control this remaining half of the intensity also from 50% to 0 by changing the angle that the path axis of the Polaroid P2 is making with the path axis of the Polaroid P1. Unpolarized light can also be polarized by the phenomenon of reflection. We know that when light is incident on a reflecting surface, some part of it gets refracted and some part of it gets reflected. When unpolarized light is reflected from a surface, the reflected light may be completely polarized, partially polarized, or unpolarized. This depends on the angle of incidence. So what I'm trying to say is that this reflected light portion is something we can control by changing the angle of incidence. We can't really do anything about the refracted light component, but because the amount of polarization of the reflected light depends on the angle of incidence, we can do something so that the reflected light is completely polarized. In general, the reflected light may be partially polarized, unpolarized, or completely polarized. Now, if the angle of incidence is 0 or 90 degrees, then obviously the incoming light is unpolarized, so the reflected light will also be unpolarized. But for angles between 0 and 90 degrees, that is, for an angle of incidence between 0 and 90, at some angle, we will be able to make sure that the reflected light is completely polarized. So how do we do this? We do this by understanding that unpolarized light consists of two electric field components. The first component is the component which is perpendicular to the plane of incidence, or I can say it is parallel to the reflecting surface when it just reaches it. Now, this component will not change in any way if you change the angle of incidence. As you can see from the figure, when the component of light which is parallel to the reflecting surface is hitting the surface, some part gets reflected and some part gets refracted. That is, the vibration of light parallel to the reflecting surface gets both reflected and refracted. And because this component has nothing to do with the angle of incidence, there will be no change in its condition of reflection no matter what you do to the angle of incidence. So I say that the vibration of electric vector which is parallel to the reflecting surface remains the same no matter what the angle of incidence. Even if you change the angle of incidence, the reflection condition will not change. So nothing is going to change about this part of the incoming unpolarized wave. However, the other component which is the set of oscillations of the electric vector which are in the plane of incidence or in the plane of your screen or in the plane of your paper. In this case, these set of oscillations or these vibrations of the electric vector, these are making different angles with the reflecting surface as the angle of incidence of unpolarized light is changed. So in this case, we will be able to change the condition of their reflection by changing the angle of incidence. Here you can see all the incoming light wave is getting only refracted and not reflected at all. So these set of oscillations, that is the component of the electric vector which lies in the plane of your screen, usually gets refracted and does not get reflected. It usually gets refracted. By changing the angle of incidence, we can change how much refraction and how much reflection takes place of this particular component of the electric field vector. So now if I study these two components together, I know that the dots are going to go up and down in both ways, but these arrows which are representing the set of oscillations in the plane of incidence, that is in the plane of my screen, they will usually get refracted, but some may also get reflected. And I know that I can change how much reflection of these is taking place by changing the angle of incidence. So what I do is I change the angle of incidence, and when I change it at one particular angle of incidence, I see that these components of the electric vector which lie in the plane of the screen no longer get reflected at all. And you see that the outgoing reflected wave is completely plane polarized. That is, only the dots are passing through and no arrows are passing through at this particular angle of incidence, and this particular angle of incidence at which the reflected light is completely polarized is known as the polarizing angle or the Brewster's angle. So here we have seen that there is a particular angle for which the reflected light will be completely plane polarized. So at the polarizing angle or the Brewster's angle, most of the vibrations of the electric vector in the plane of incidence get transmitted and are not reflected. Hence, the refracted light which has gone into the medium, that is, you see that it has both dots and arrows, and therefore it's a mixture of polarized and unpolarized light. That is, it is partially polarized light, but the reflected light is completely plane polarized light. The reflected light contains vibrations of electric vector perpendicular to the plane of incidence only, because all the ones which were in the plane of incidence disappeared at the polarizing angle. At the polarization angle, it is also important to note that the angle made by the reflected ray and the refracted ray is 90 degrees, and this is Brewster's law. So this means that the reflected light is completely plane polarized in a direction perpendicular to the plane of incidence at the Brewster's angle or at the polarizing angle. Thus, we have shown that polarization of light can also be obtained by the phenomenon of reflection at the polarizing angle. So this completes all the topics that I want to talk about under the umbrella of diffraction and polarization of light. I hope you enjoyed this video. Thank you for watching. Thank you for watching this video. If you like our channel, please click on the subscribe button which is given right here on my right. And if you want to buy your very own target book, you can also click on the link given below. Please stay tuned for more updates.